So as I was saying, since K is a group on one cation, it's always going to be soluble based on our AP Chem solubility rules. So in this overall equation, it's not going to be like the previous example that we looked at with magnesium hydroxide. Magnesium hydroxide is relatively insoluble, but potassium hydroxide is soluble. So we do not show it as a solid in the overall net ionic equation. So even though it is completely soluble, it says that we start with a solid, so that's why on the reactant side I do have K2O solid. It's not aqueous yet. It specifically says that we're adding it to water to form a solution, which is going to have 2K plus ions and 2 OH minus ions in the solution. Other ions that are extremely basic, like O2 minus, that will strip away a hydrogen ion from water, would be N3 minus and NH2 minus. Okay, so those are other ions that would, again, strip away that hydrogen ion from water. Some salts do have an acidic cation and a basic anion. These salts tend to have little or no effect on the overall pH. So here we have a salt with a acidic cation and a basic anion, okay? So this C2H3O2 minus will accept an H, whereas this NH4 plus will donate an H. So it doesn't really have a huge effect on pH, because while for a moment this NH4 will donate H8 plus, releasing it into the solution, pretty quickly this base will accept it. So there's overall no change in pH when this happens. You can look at Ka and Kb values that are given, if they are given for an acid or base, to compare it to figure out if a solution is acidic or basic. So the next unit, which covers acids, goes into more detail about Ka and Kb values, but basically it's an equilibrium constant for an acidic substance or a basic substance. That's what the A and B stands for. So if the Ka is greater than a Kb, the solution is going to be relatively acidic. If the Kb is greater than the Ka, then the solution is relatively basic. So here is another example with copper 2 fluoride. The copper will donate an H plus or proton, and the F minus would accept that proton as well. The solubility of slightly soluble salts containing basic anions, increases as the concentration of H plus increases. So basic aqueous anions will accept those protons from the acidic solution, and it results in a strong acids. So if we consider magnesium hydroxide, I said before it has a pretty low solubility, meaning if you put it in water, you wouldn't see it dissolve, but there might be a few ions of Mg2 plus and OH minus that do escape into the solution, but it is a very, very low solubility. If we consider adding an acid to that solution, specifically a strong acid, what that does is it adds H plus to the solution. It would also technically add something else, whatever went with that H plus, whether it's SO4 minus or HCl, or Cl minus. There is going to be something else there, but usually we won't show that in the equation because it's a spectator ion that's not going to react with anything else. It remains in an aqueous solution. So we'll just say that we added HCl to the solution. What that did was increase the concentration of H plus. How does that affect anything? The H plus is going to react with OH minus, these OH minus, which then shifts the amount of the concentration of OH minus. If we decrease this concentration, according to Le Chatelier's principle that we talked about, that would be lowering the concentration. The equilibrium will then shift to the right to produce more products. that means that the solid is going into aqueous ions more. So it would then increase the solubility by shifting that equilibrium. Okay, so then the net ionic equation comes out to be this. You basically cancel your two OH minuses, so you get MgOH2 solid plus 2H plus, yielding Mg plus and 2H2O. So again, there might be Cl minus or some other strong acid that went with that H, but it's kind of left out of the equation. We don't really care about it because it doesn't really react with anything. What's reacting is that H plus to reduce the hydroxide ions in the solution to increase the solubility. So if we have solid calcium carbonate placed in a solution of hydrochloric acid, we want to write the net ionic equation for the overall reaction. So the first reaction I'm going to write would be between the dissolution between calcium or in calcium carbonate into its ions. So calcium carbonate is CaCO3. It would dissociate into Ca2 plus and CO3 2 minus. Okay. The next thing I'm going to do is consider hydrochloric acid. Hydrochloric acid is HCl. It's made up of hydrogen and chlorine. And like I said before, the chloride is going to end up as a spectator ion. So it would probably react with Ca to make CaCl2, which is soluble. So it would remain aqueous in the solution. So I'm going to ignore that chlorine, basically. And I'm going to consider H+. Looking at these two products, which species is H+ going to react with? It's not going to react with a cation because it is a cation. So remember, opposites attract. So it's going to end up reacting with this carbonate ion. So when that happens, it's going, in order to balance out, you do need two H's, and it's going to make H2CO3. Whenever we get H2CO3, it's a carbonic acid. It's just something about carbonic acid that's special is it always breaks up into CO2 and H2O. So carbonic acid, H2CO3, is relatively unstable. It's always going to break up into water and carbon dioxide. So you could write that equation if you want, or you can just remember in the overall net ionic equation to write that instead of H2CO3 aqueous, okay? But whenever you see H2CO3, remember it's going to break up into water and carbon dioxide, okay? So when we add these two equations together, the CO3 2 minuses are going to cancel out, and we end up with CaCO3 solid plus 2H plus, yielding Ca2 plus, H2O, and CO2. And again, that H2O and CO2 came from the carbonic acid. So here's another example. We have solid magnesium oxide added to a solution of nitric acid. Write the net ionic equation for the overall reaction. So the first reaction I need to consider is magnesium oxide breaking into its ions. So we've seen magnesium oxide before, it's MgO. It would break into Mg2 plus and O2 minus. Now nitric acid, I have to consider what part of the nitric acid is important. If you remember from naming acid, nitric acid is from the nitrate ion, so NO3. So it's H plus NO3. Or HNO3. So which part of that nitric acid is going to be important is the H+. Between these two, which one is H+ going to react with? It'd be the O2-. And again, because it has a 2- charge, you would need two H+. So the other equation we're going to consider is this one. And we end up with liquid water, which, as we know, is pretty stable. So it's not like the carbonic acid where it's going to break up into anything else. Now, if we add these two equations together, the O2- are going to cancel out, and we get MgO solid plus 2H plus, yielding Mg2 plus and H2O. Okay, so we can also consider solubility and weak acids. So we just considered strong acids. Just like with strong acids, the solubility will increase for the exact same reason. Even the small amount of H+ that goes into the solution will remove some OH-, keep doing that, thus shifting equilibrium to the right, increasing the solubility of this salt. The difference really lies in how we write that second equation. So here, sorry, wrong way. There we go. There, I didn't write nitric acid HNO3. I just wrote H+, because it's a strong acid and it dissociates 100%. Weak acids do not do that, okay? So I do have to write the entire weak acid when considering that. So that's going to be your biggest difference. So here's a weak acid. It will again react with the OH-. The H, two H's really, will leave to complete two waters and leave us with CH3CO2-, which would be a strong base. So this reduces the concentration of OH- in the solution, which drives the equilibrium to the right, increasing the solubility of magnesium hydroxide. If you add these two equations together, the net ionic equation is MgOH2 plus 2CH3CO2H, yielding Mg2 plus 2H2O and 2CH3CO2. Okay, so again, this is a weak acid. Whenever there's a weak acid, we can't just show H+ because it does not dissociate 100%. It tends to favor this form. So here's an example. We have solid calcium carbonate in vinegar. Write the net ionic equation for the overall reaction. Since there's a carbonate, keep in mind that if you get carbonic acid, it will break up into H2O and CO2. So first I'm considering calcium carbonate. It's going to break up into its two ions, Ca2+ and CO3 2-. If it is placed in vinegar, that's acetic acid, so I have the acetate ion with H. So I have 2 CH3CO2H plus CO3 2-, and I know I have 2 of those acid molecules, really 2 moles of those acid molecules, because I have a 2- charge on the carbonate ion. So that will form H2CO3, again, that carbonic acid, which will break up, and then 2 acetate ions. So if we balance this equation, you'll notice that the carbonate ion will cancel out. So we end up with COCO3 plus 2 C2H3O2H, yielding Ca2 plus H2O and CO2 that comes from the carbonic acid, plus 2 CH3CO2-. Okay, so that is solubility in acids and bases. Basically what happens is the acid or base, you need to think about how it's going to affect the ions that are formed in that solution. You just have to know what ions are more likely to react and behave like an acid or like a base, okay? Later this week I will do some titration, a little bit more acid-base notes, because it's kind of it's kind of weird because acids and bases are covered in Unit 8, but it's also kind of fair game because we also cover them in 4.8 and now. So I just want to cover a little bit more on acid bases before you take the exam on Thursday. But let me know if you have any questions. There's a worksheet to work on, and I also have a short practice exam for us to kind of take tomorrow to get into exam mode. So have a wonderful day.